All right, so let's go over Booth's multiplication algorithm, right? So yeah, I'm not necessarily going to go over like the exact theory and all that nonsense. Let's simply just start right away with a nice little question, a very amazing question here, which is, what is 7 into 5? That is the big question here today, and maybe I'll do another question as well, just to take negative numbers as well. Essentially, how is this calculated within the CPU? That is what we're actually going to go after. Right now, what happens here is that this 7 here, now this is how the process actually goes. So before we do anything, of course we have to write these in binary, and we give them special names. So 7 is the multiplicand, right? So you write it as m and you say m is 7. How do you write 7 in binary? So 0 1 1 1, of course, and that's basically good enough. Then the next question is, what is q? Q is 5, right? So how do you write q 5 in binary? So 5 is simply 4 plus 1, right? So that is basically what you would write. Good enough. We can start here and we can come back whenever there is an issue or whatever. Okay. So the process is very simple. So we look at the number of bits here. So only 4 bits are used. So that's completely fine. That means that we will have 4 bits in the accumulator, and we copy paste the q into the q register as well. Accumulator is simply a register where these sort of operations are done, right, and where the CPU sort of keeps the intermediate results and all that stuff. So that is what the accumulator is. The q register is a special register here, right? Okay, all right, now we have to decide how. Before that, we also actually what happens with this q register is we also just consider another value, which is the q minus 1th bit, which initially is a 0, right? Eventually it will get its own values, but right now it just has a 0. Now we look at the size of q. So q has 1 2 3 4. It has 4 bits, therefore we say that we have to do 4 total iterations. Okay, let us begin now. Actually, before we begin, I want to simply clear up a certain thing. So we always, now this is extremely important, because this is what the algorithm will kind of depend on. So this bit here, in the last bit in q, the LSB, least significant bit here, is called, we will just call it q, right? I know it causes confusion, so I guess I can just call it q0, right? And this bit here, the 0 that we have added on as on top, is q minus 1. They can of course have 4 values, 0 0 0 1 1 0 and 1 1. Now you have to do some very specific operations whenever you see these specific values. So if there is a 0 0 combination going on, you do not touch the register at all. You do not touch the accumulator stays as is. If you see a 1 1, the accumulator stays as is. Now you might probably already get it that you do certain things when you see these 0 1 and 1 0 cases. So what do? When you see a 0 1, you are supposed to put inside a plus m. When you see a 1 0, you are supposed to put inside a minus m. Okay. Now this raises an interesting question that I just want to bring up. Okay, so you notice that there is one particular case where you have to do a gives a, like you have to put inside a minus m. Now think about it like this. So just consider this case. So you have a 0 0 0 0 right now in the register, right, accumulator. So you put 0 0 0. Now if I ask you to subtract m from the register right now, so you'll diligently write down subtraction with 0 1 1 1. How do you actually do this? Right, so how do you subtract from 0 0 0 0 a minus 0 1 1, right? So this stuff becomes very complex and weird. Some people might feel very inclined to simply write minus 0 1 1. I understand where they are coming from if they do this, but this is not what you're actually supposed to do, right? So there is a very specific way to handle this, right? And a very natural way to look at it as well. So look at this. So a minus m, if you think about it, a minus m is simply a plus minus m. Now I'm not playing around with symbols, right? There's a specific reason why I'm doing this, and this is also used in adders to actually implement subtraction as well. If you have studied, you know this, right? I of course do. So yeah, anyways, so minus m, right? That means that you're simply adding a minus m to a, right? This is now an addition operation. Then the question is, okay, I kind of have just shifted the goalpost, but what is minus m now? Because you still do not have minus m. The answer is minus m actually is found by taking the 2's complement of 7. Now what is 2's complement? 2's complement is simply the 1's complement plus 1. So how do you find up 2's complement here of m? So I'll just write it here. Now minus m is going to be equal to 2's complement. And for that, first we take the 1's complement of 0 1 1 1, which is simply you just take a you just take a complement of all of these bits and you flip them and you write 1000. You don't stop here, however, you add a 1 to it as well. That is the standard procedure, and you get 1001. This is what minus m is. And notice how you don't actually have to perform any subtraction now. You simply have to perform addition, which is extremely easy, right? There is no complexity in addition. All right, then I think we are basically ready to begin. So how do we begin? Let's begin the the first iteration. So you notice the q0 bit and you notice the q minus 1 bit, and you see that there's a 1 and a 0 here. Now 1 and a 0, look at this table here. So when you see a 1 and a 0, you are supposed to perform, you are supposed to put in a minus m inside a. So let's calculate, right? So let's calculate. So you have 0 0 0 0 and your minus m here is 1001. When you add them, what do you get? 1001. Amazing. There is nothing crazy or new here. So we'll simply say that the resultant of that is 1001. Let me write that properly. 1001, and that there will be 0101 along with that q minus 1th bit. There is no reason to write it, but I'll do it, right? And now to finish this particular iteration, right, we are not done yet in order to finish this iteration. So what we will do now is we'll perform a right shift by just 1 bit. Now before you do it in a hurried fashion, because I know the sort of idea will be that you'll just stack a 0 here and write 100 and proceed. That is wrong. You have to notice that you have a 1 here, and this MSB always represents the sign. Since this is a negative number, you do not want to miss the sign, right? You don't want to, you can't just lose your negative symbol. You have to keep your negative symbol, and then you do the copying right shift nonsense. So 100, and then this one that you have goes into the queue. So 1010, and now you might ask what happens with this one. Well, nothing. It goes inside the q minus 1. So you get a 1 here. Now we say that we have 3 iterations left. Okay, now we are at the start of the second iteration. So notice how we have a 0-1 combination here. So what do we do when we see a 0-1? There is no need to look at the table, but sure, when you see a 0-1, you have to perform addition, a plus m. So a right now is 1100. What is m? The value of m is 0111. So we'll write 0111 here, 0111. 1 plus 1 is a 0, 1 carried. So 1 plus 1 is again a 0 and 1 carried. We dump the extra carry bit, we don't care. We look at this new value that we have and we say 0011 is what is inside the accumulator. The q still is the same, 1010. The q minus 1 bit doesn't change, but still is a 1. Okay. Now in order to end this iteration, of course, we still have to perform the right shift. Now notice how this time the numbers that we have, this time the accumulator is actually positive because the MSB is a 0. So we still copy the 0 and then we perform the copying operation. The shifting operation. So 001 and then 1101, right? And we get a 0 here in the q minus 1th bit. Now we say that we have 2 iterations left, right? It's very simple. Now let us begin the third iteration, right? So you will notice now that you have a 1 and a 0 here, which means again you have to perform subtraction, right? I think we already wrote that here. 10 implies subtraction. So how do you do that? You simply take 0001, the current value in A, and you take a minus m. Where is that? 1001. You perform the addition. So 1 plus 1 is a 0, 101. So 1010 is what the value actually is. So you write that here. So the intermediate value is 1010 and 1101 inside the queue sort of stays the same. That's what it is. Now in order to finish this iteration, of course, we have to perform the right shift. So again, notice that this is a negative value. So you have to simply write a 1 here. That's what the rule says. And then you have to perform the shifting 101, 0, 110. And then you take this one that becomes the q minus 1th bit. And now you say that you have 1 iteration left. Right? Amazing. Whew. Okay, let's look at q0, let's look at q minus 1. They are 0, 1, and again when they are 0, 1, you have to perform addition, right? A is equal to a plus m. So look at a, that is 1101. What is plus m? Plus m is 0111. 0111. 1 plus 1 is a 0, 1 plus 1 is a 0, 1 plus 1 plus 1 is a 1, carry 1, 1 plus 1 is a 0, and 1 goes here. We dump this extra 1, we don't care. So we write that the intermediate state now is 0100. And this still stays the same. and then there's a 1. Now of course, in order to end this particular iteration, we have to perform the right shift, which leads to, now again notice that the MSB in A is a 0, so we just have to copy that first and then perform the shifting. 0 1 0 0 0 1 1, and then there's the q minus 1 bit becomes 0 now, and now we say that we have 0 iterations left, which means we can terminate our process here. This is the final answer. Now you might ask, what does that even mean? You know, is this the answer or is this the answer, right? Which of these registers are actually the answer? And to that I say, like, think about what multiplication actually does. So if you do 10 into 10, for example, it becomes 100. Notice how the number, you know, the number has actually become like incredibly huge. So to write 10, you may require like just 3 bits, right? Or not 3, 4 bits. To write this 10 also you might require 3 bits, but to write 100 you'll require a lot more bits than just, you know, 3 bits or 4 bits, whatever it is. So that's kind of how I see it, and with that we can say that this entire combination here that you have written here, A and Q, you concatenate them and that is your answer essentially. So 0 0 1 0 and 0 0 1 1 is the answer. That is the answer. Now what is the answer then? Let's verify. So that is 1 plus 2 plus 4, 8, 16 and 32. What is that equal to? 32 plus 2 plus 1 is simply a 35. Now is that correct? Let's check. So the original question was 7 times 5 is equal to, and we got 35, and clearly we can use calculator, multiplication table or whatever, and yeah, this checks out. This is correct. So this is the answer, right? I think this whole process is quite neat and fun, and yeah, that's basically about it. I'll do another example with a negative number now.